Good afternoon. This is Andy Schweitzer, and this is an introductory to ionic bonding. Again, there's entire books on ionic bonding, so this is really just a real basic introduction to ionic bonds. Some of the things I think are the bare minimum things that you might want to know. All right. So why do things bond in general? Again, same as you might have heard before is when something bonds, it is trying to lower its energy, in the process becoming more stable. Again, this is the same reason why a ball rolls down a hill. Because and it does it on its own. It will roll down, it will release energy all along the way, becoming more stable. So things that release energy are generally spontaneous and generally are more stable. Can the ball roll back up the hill? Well, of course it can. It's just not going to do it on its own. You need to drive energy into the process continuously to get it back up there. Both processes are legitimate. One just requires energy to drive it, one gives away energy. A process that requires energy to be fed into it all the time, we call endergonic. And of course, this is called exergonic. Okay, so when a reaction happens of bonding, it's just because it's releasing energy in order to become more stable. That's if it happens on its own. There are bonds that can occur that people are, or the environment or whatever is feeding it energy so it can continue. But again, why is it a bond? Because it's on its own become more stable. The next one, so for ionic bonding, a few things you want to know, and I'll be covering sort of in this thing here, is what atoms ionic bond. That sounds strange. I could put it what atoms ionically bond, but I don't know if ionically is a word. So why do they ionic bond? Now again, we mentioned this already, that this is answered to become more stable. So that's, in the end, what we'll leave it as. How do they ionic bond? So we'll look a little bit at the function of how this works. And then what are some consequences of ionic bonding? So real standard. Let's look at what atoms ionic bond and just some of these things. So, of course, again, if you see an atom or a substance, you should know whether that substance is capable of ionically bonding. So we have a periodic table. Okay. Of course, we have our metals from our nonmetals. An ionic bond is a bond between, again, ionic meaning ions, is a cation and an anion. Okay. So in that case, however they happen to become positive, or how they happen to become negative, that's at some point may not matter, but you should be aware that metals tend to lose electrons to form cations, and that nonmetals, okay, gain electrons to form anions. One's positive, one's negative, and therefore this is going to attract by Coulomb's law. Force of attraction is proportional to the charge of the cation, charge of the anion, divided by the distance between them. So, just again, without digging too deep into things, can you recognize ionic bond compounds when you see them? That is going to be a bond, generally speaking, between a metal and a non-metal. Okay, metal and non-metal. We'll see a few reasons as to why, but their formulas will also be empirical. which means it'll be the simplest ratio of atoms. Now, examples. NaCl, 1 sodium for every 1 chlorine. Magnesium fluoride, 1 magnesium, 2 fluorines. Okay? Metal, nonmetal. Metal, nonmetal. You will note that they are also charge balanced. So you have positive 1, minus 1, positive 2, minus 1, and there's 2 of them. So in this case, we have situations where we have metals and nonmetals, cations, anions. Is there a possibility of having where it wasn't a metal and nonmetal? Okay, let's try magnesium nitrate. Again, it's charge balanced. This guy is a minus 1 charge, so there would be 2 of them to charge balance off of the magnesium. This is a metal cation. This is a anion, which is a unique substance that happens to have a negative charge. This is my cation. This is my anion. You should note that nitrate itself happens to be covalent. And it is a molecule that happens to have a negative charge. And that attracts to a positive magnesium ion. Okay? So it doesn't always have to be a metal and a nonmetal, but a lot of times, again, you have to recognize these guys as well. They're called polyatomic ions. Okay. Another example, which would be, let's say we have ammonium. Let's say ammonium chloride. This is a positive 1. This is a minus 1. Of course, you have to recognize that this is a polyatomic cation, and that this has covalent inside of it. But that the whole thing is ionic. It is a molecule, it happens to be positively charged, and it is attracting to negative things. This case happens to be chlorides. This traction we've seen right here and right here is just Coulomb's attraction. Force equals charge of the cation times charge of the anion divided by the distance between them squared. Okay. So now the next thought here is, okay, what items ionically bond? Metals, nonmetals, cations, anions. You should be able to recognize these things. Okay. All right. How does it do this? Well, simply how they do it is going to be they're going to transfer electrons. Now, let me clarify this question: is how do you ionically bond? Well, you could even say that this is very simple. Ionic bond is just a positive attracting to a negative based off force equals charge of the cation, charge of the anion divided by the distance squared. But if we want to dig a little deeper and say, okay, how do we get cations and anions? Okay, that might be a little bit more in-depth question and could lead to greater understanding. Okay, I will note here that generally, okay, metals, this is important, metals, if I were to draw a Lewis structure of this, say a Lewis dot diagram, we have metals, we have non-metals. All right, so we have sodium, which has 1 valence electron, magnesium, which has 2 valence electrons. Kicking over here, we have boron, 1, 2, 3, carbon, 1, 2, 3, 4, nitrogen, 1, 2, 3, 4, 5, oxygen, 1, 2, 3, 4, 5, 6, and then we have fluorine, which is 1, 2, 3, 4, 5, 6, 7, and then of course we have neon, which is 1, 2, 3, 4, 5, 6, 7, 8. The premise behind this, all of this, is that, again, a full outer shell is more stable. So this thing is going to do whatever it can to acquire that. Okay. Now it turns out that for covalent compounds, they'll share to fill the outer shell, but in this case, we are simply going to have a transfer of electrons. If we have, let's say, sodium, which is going to be, let's say, as one valence electron, is neutral, and then we have, let's say, fluorine, which has 1, 2, 3, 4, 5, 6, 7 valence electrons, is in fact neutral. Okay. Neither of them are stable. Okay. But in this case, the sodium will be ditching its outer electron because it only has one. It can either fill it with 7 more to get full, or it can lose the outer to expose a full inner shell. In this case, as it loses electron, again, losing electrons is called oxidation. So metals oxidize to form cations. And then the anions, the nonmetals, will pick up the electrons. Okay, so nonmetals gain or reduce to form anions. Okay, so in the end, this whole process will form Na plus and F negative. And just because this sodium gave this fluorine its electron doesn't premise the bond. The bond is premised by the fact that this is positive, this is negative, and they attract. In fact, this negative will attract to other positives, which in that case could form in all directions. And in fact, it does. Okay? And we can have all sorts of positives and negatives attracting to each other. It's not orderly, okay? It's just a big, large process. Now, from this process, what I would maybe mention, okay, is that, and sometimes I use this to explain it, is that if you're on Earth, okay, you have a person on Earth, okay, and you know, if you're standing here, and there is a pile of dirt right here, okay, and of course I say, well, if there is a pile of dirt right here, then that means that somewhere there has to be a hole. Okay, same thing for positives and negatives. If you have one thing that is positive, then you have to have something else that is negative. Then they have to be equal. Okay, this is an accumulation of the protons and of the electrons, and you can't. They come in equal amounts. So if one item becomes positive, there has to be a negative associated with it, and that is critical. Okay, and by equal amounts. So we can't have in a solution only cations. We can't have in a solution only anions. The cations and anions will be equal in charge quantity. I could have a whole bunch of positive 2s, and I could have double the minus 1s, but in the end, they have to have the equal charge balance. Cannot have a positive without having a negative. All right. All right. So the last little bit is, what are the consequences of ionic bonding? All right. The biggest thing I try to premise is what's called the bulk crystal. Give me a second here. Okay, and this is going to go to its counterpart, which is the molecule. And you should see the very big difference. Okay. Now, a bulk crystal is a cation, an anion, And because they're different charges, and given the opportunity, if they're allowed to move, these guys will attract, and the positive and negatives would attract, and the negatives would repel, and positive repel. But given the opportunity, this thing will order itself. Again, I don't want to act like those are bonds or still be showing attraction. All right, in all three dimensions. So this is a bulk crystal. It is simply what I refer to as a pile of cations and a pile of anions. If you split it in half, right down the line here, you still have a same thing here as you do over here. You can break this bulk crystal in half, and it really is no different. Pile of cations, pile of anions. It is for this reason that we call it NaCl. It's giving us what's called an empirical formula. Okay, that is the simplest ratio of atoms. For someone to write down, let's say what students quite often write out ionic compounds. So we'll say, okay, well, what if we have sodium chloride? So +1, -1, so that gives us sodium chloride. Or we might write down calcium chloride. Okay, well, there's +2, -1, so this gives us calcium chloride. And let's say we have calcium oxide, +2, -2. This gives us calcium oxide. So there's a couple things here that people just, when I see them make mistakes, tells me they truly don't understand the overall process. Okay. Now, in this case, sodium chloride, all right, means there's one sodium, one positive for every one negative, and they come in 1-to-1 ratios. Does not tell us how many, or actually there could be bazillions of them there. We don't know. They just come in a 1-to-1 ratio. In this case, it means we have, when electrons were transferred, the calcium gave up 2 valence electrons, and the chlorine could only pick up 1. That's fundamentally how this worked. So we have the calcium produced 2 anions versus the 1 calcium +2. They come in a 1-to-2 ratio. Okay. Calcium oxide. All right. Again, the calcium was able to give away 2 electrons, but the oxygen, it was right on par. It simply picked up 2 electrons, forming a calcium +2 and oxygen -2. Forms a calcium oxide. It would make no sense to write this as calcium 2 oxide 2. This is not a reality. It happens all the time. All right? And you have to understand that there is no molecule here. There is no unit that this would indicate that there is somehow 2 calcium particles clumping with 2 oxygen particles, and that's forming a little unit. That is not the case. It is simply a big pile of cations, a big pile of anions, and they're all attracted to each other based on the size of their charge and the distance between them. So we would never write this as Na2Cl2, even though it could be. All right? Is there 2 sodiums or 2 chlorines? Yes, but you're insinuating a molecule here, which is not the case. A molecule is covalently bound and is basically can survive on its own. Okay, it's a unique compound, a unique substance. An ionic bond, pile of cations, pile of anions. It is possible to have the two mixed together, where you could have, let's say, a calcium +2 ion and a hydroxide ion. So in this case, this is covalently bound and it forms a little molecule. Again, did the calcium actually give its electrons to the oxide? We don't know. I don't know. All I know right now is I have calcium ions and I have oxide ions, hydroxide ions. So we would have positive, minus, positive, right? We'd have, in this case, it would be CaOH parentheses 2, okay? Because this is an actual unit that's actually together, we put it in parentheses to show there's 2 of them, Okay, so I have to have 2 of my negatives for every 2 positives for a positive like this. Okay, this is a +2, +2, and it look like that. Okay, forming in that ratio. But again, we just still, it forms different little crystals. Okay, but in the end, it's still the same way. Okay, big pile of cations, big pile of anions, and give the opportunity to form a little crystal, and they just attract to one another. Keep in mind, inside of that negative, there is this guy, a covalent molecule that happens to have a negative charge, and therefore happens to attract to calcium ions, which are positive. And the hydroxyl will attract to any positive. It doesn't have to be calcium. So, writing out ionic formulas, we have to understand they are charge balanced and the usage of parentheses. Thank you.